No, sir.
Some of you came on Thursday? I know that I told you in the class that there will be a class on Thursday, but then after I came here, I realized that there was a holiday on that day. So let me review a little bit what we had done. In the previous class. Okay. So here it is. So last time, that is the final lecture I wanted to take on the tools. We've learned two types of things. One is vectors and tensors, and the other is this simulation method. And today I'm going to talk a little bit about slow flows. So we got introduced to lamps. And the last example that we were looking at was this flow down an inclined plane, which is the same as looking at the flow in a rectangular box, which is shown here, but with the gravity pointed in at an angle. And then there was another program to analyze the data that we got from this. And then this is the script where the main additions are that you have periodic boundary conditions in the direction of the flow. There are two types of particles. The moving particles, which are given in this data file, posrel.data. And then there are the base particles, which is in base.data. And these are static. So, and we can name these groups also. These particles are in the group mobile and these particles are in the group static. And so when we specify which particles have to be integrated, we only say mobile particles are to be integrated. And then we have put the gravity vector also at an angle. And then the rest of the program is the same. And we saw that we can start from this and then, you can get a steady state, a layer of particles flowing on. And of course, the particles right at the bottom are the base particles. You can see the blue ones are the base particles. And this is what it looks like when they're flowing. And if we do the binning and all these kind of things using that program cg.c, then you can get the one on the left is the volume fraction profile, and then the one on the right is the velocity profile. So you can get all sorts of very detailed information for the flow. So with that, we wanted to end the lamps thing, and now I want to talk about very slow flows. You remember we defined the inertial number. So the inertial number is very small, and so frictional forces are dominant. And here I just wanted to first discuss, how we can calculate the stress tensor and on different surfaces within the system. And then I'll define something called principal axes. And in those along, that's two axes where the stresses, normal stresses are maximum or minimum. And then, how we can represent the stresses in something called Morse circle. And based on that Morse circle, we can define a yield criterion also. So supposing you put pressure on a set of particles, a bed of particles, then when will they yield and start flowing? So those are some of the things that we will start looking at. Okay. So has anyone had a chance to look at some of the programs and so forth? Okay, so let's start. Did anyone look at the program? When I hear the silence, does that mean that nobody has had a chance to look at it? Okay, so we'll start. This is the 12th lecture. And today is 23rd. Okay. So as I was saying that, really we want to look at granular materials which are either static, they're just not moving, or they are moving very slowly. And in this case, what happens is that the particles will be all the particles will be in contact with each other. And since they are not moving, I mean, the only force that is acting between the particles will be frictional forces. So either we'll look at static systems or very slowly moving, which I'm calling quasi-static. And here you have inertial number. If you remember, it is I, which is defined as shear rate gamma dot D divided by the pressure divided by the particle density raised to the power of half. So this is a dimensionless number which says how rapid the flow is. And if this number is very small, then we say that it is a slow flow system. If it is more than 0.1, then we say it is rapid flow. So we are looking for this, either this is much less than 1 or much less than or I is equal to 0. That means that there is no flow at all. And in this case, we are looking at systems where particles are essentially just touching each other in this way. And because of this, the only force that's acting is friction. And of course, deformation and all these things are also important. But so this is the kind of system that we want to analyze. And we are not really interested in this particulate picture. As always, we would like to sort of consider a continuum. That means we have very large number of particles, and this essentially looks like a uniform solid or a continuum. And we discussed what is a continuum a little while before. So we want to just look at a stress at a point. And in this, let's suppose we want to calculate the stress tensor. I mean, suppose the stress tensor is given as this, and we want to calculate the stress on a surface. So let's say the stress tensor sigma is just given as sigma ij ei ej. Now we have already seen what this means, and essentially I and j are the components. There are two directions which decide what are the components of the stress tensor. So if we, let's say, do sigma dot E1, then this is nothing but the stress vector acting on a surface with a unit normal E1. So this is what is the definition. We have already seen that if we take a dot product between a tensor and a vector, you will get a vector. So what you can imagine is that, let's say this is the surface. Okay, there's always surface. Whenever we think of stress, we always have to think of stress acting on a surface, because it is stress, it is force per unit area. And then let's say on this surface, we have a unit vector which is E1. Then the force that is acting on this surface let's try it this way. So let's say this is the force that is acting on the surface which has this unit vector. Then this force is just sigma dot E1. And then if we take, let's say, this direction to be E2, the second coordinate direction, then sigma dot E1, and then we dot it with E2, then this is nothing but the stress. Now this is a scalar quantity, acting in the direction E2 on a surface with unit vector E2. So you can think of this as, take the projection of this here. So this is given by that. So here is the first part of our tools coming into action. We are seeing how we can use vectors and tensors to better understand, in some sense, the physical meaning of various things. So whenever you take a dot product of a tensor with a unit vector, then it will just give you a vector. And in this particular case, it gives you a force per unit area. Force is the vector. And that force per unit area acting on this surface. And then we can take, whenever you take a dot product of a vector with another unit vector, then that gives you the component of the vector in that direction. So the component of sigma dot E1, which is a vector in the direction E2, you have to take a dot product with E2, and so you get this. So in some sense, what we have managed to do is, if you write down this, then this, if you open out everything, this is nothing but sigma 2,1. So this is the meaning of the component sigma 2,1. And similarly, if we had taken then again we'll get a scalar quantity, and that is sigma 1,1. And so this is nothing but a shear stress, and this is a normal stress. And if we say in physical terms, E1 is the surface on which it's acting, that is, the surface is normal to E1 and it's acting in the direction E1. So, if we had to take the same thing and draw it, then it will be this vector. I should draw it the other way around, sorry. But anyway. I should draw this because it's acting in the direction E1. Okay. So this is the normal stress, which is the force per unit area acting on a surface with unit vector E1 in the direction also of E1. So if the surface vector and the direction of the force is the same, that's a normal force. And if the surface vector and the direction are orthogonal to each other, then it is a shear stress. So in this way, we can calculate the shear stress and normal stress, in fact, all the stress components on any surface. So now, supposing I'm given this stress tensor, and then I want to calculate in my system, let's say these are my coordinates, and I'll call it as Ex and Ey. which is E1, E2, it's the same thing. And so this is my coordinate axes X and Y, and these are my unit vectors Ex, Ey. And suppose I want to calculate within this system, I have a surface, and I want to calculate what is the force acting on this surface. And I'm given that the normal vector to this surface is, let's say, n, and the tangential vector is t. And let's say the normal vector makes an angle alpha with the x-axis. And actually, I can just define this as a new coordinate system, x prime and y prime. So it's as if I've changed the coordinate system to a new one, x prime, y prime. So in this coordinate system, it's easy to see that the normal vector n, if we just do a little bit of geometry, you will see that n is just cos alpha Ex plus sin alpha Ey. So we can write this normal vector, we can take the two components of it, and you will get these two. And similarly, the tangent vector t is equal to cos alpha Ey minus sin alpha Ex. And as a check, just to say that it's correct, if you say put alpha equal to 0, then n will be along the direction Ex and t will be along the direction Ey, and that we get. And if alpha is 90, then n will be in the direction Ey and t will be in the direction minus Ex. And so those two things are also done. So it satisfies this. So now for any given alpha, I can find out what is the normal stress on this surface and the shear stress on this surface. So we can calculate this, the normal stress, and that we have already seen. We want to calculate the force on the surface, force per unit area on the vector n, so that sigma dot n, and we want to take the component of the force in the direction n, so it's just sigma n dot sigma dot n, which we can call either sigma nn, or here I'm going to call it as sigma x prime x prime. Now what is that equal to? This is, if you take the dot products with this, so this is equal to n I E I dotted with sigma k L E k E L dotted with, let's call it as NP EP. So here we take the dot products with the two closest unit vectors like this. And so this will give us Ni, Np, sigma KL. These are the scalar parts. And then I'll have delta I K, delta L P. So we know from the definition of the Kronecker delta that this will be 0 unless I is equal to K and L is equal to P. So if we make the simplification, then we can simply write n k n l into sigma kl. So we are looking only at a two-dimensional case. So k will be either x and y, and similarly l. So if we expand this, this will be nx squared sigma x, both k and l are x, plus ny squared, both k and l are y. Then you'll have two of them, nx ny sigma xy plus ny nx sigma yx. So now we know what is nx. Nx is cos alpha and ny is sine of alpha. Now we will always look at sigma is symmetric. With the stress tensor, we'll always look at symmetric stress tensors, which basically means that sigma is equal to sigma transpose. So basically, this means that sigma yx is equal to sigma xy. So from this, if you make all the substitutions, so you get sigma x prime is equal to nx is cos alpha, and so you get sigma xx cos squared alpha plus sigma yy sine squared alpha, and since both these terms are equal, and so you will get plus 2 sigma xy sine alpha cos alpha. So this is, so what I've done is nothing much. There's no physical principle here. All I've done is that I have said that, okay, if I'm given sigma xx, sigma yy, and sigma xy, that is, if I'm given this matrix, then can I calculate what is the normal force on any surface in the system? So, this essentially tells us how the normal force will vary in the system. Okay. And as alpha changes, you can see sigma x prime will change. And when alpha is equal to 0, you'll see that sigma x prime is equal to sigma xx, because this term will be 0 and this will also be 0. So, and in a similar way, you can show that we can define sigma x prime y prime as just t dot sigma dot n, which is equal to sigma tn, which, if you do exactly the same sorts of things, you can show that this is equal to half of sigma yy minus sigma xx into sine of 2 alpha plus sigma xy cos of 2 alpha. Okay, so this is the other one. And I write it again, sigma x prime y prime is just equal to half sigma yy minus so here you have this. So we can get the normal stress and shear stress on this surface for any angle alpha. So as I turn that angle, when alpha is 0, sigma x prime is equal to sigma xx, and sigma x prime y prime is equal to sigma x5, because when alpha is 0, this is 0 and this is 1. So but as I change alpha, then both the shear stress and the normal stress will change. So what I would like to do is, I would like to define some axes on which the normal stresses are 0. So those are called the principal axes. And if you look at the formulae, since these things contain cos and sine, you can imagine that as alpha is changed, the stress will have this kind of oscillatory behavior, that it will be high in some places, low in some places, and so forth. So we can find out we can expect that there is a maximum and a minimum. And the principal axes are essentially the coordinate axes in this new coordinate system x prime y prime, on which, or let's say for which, so they're defined in this. The normal stress is either maximum or minimum. Now, here is the formula for our normal stress. If I want to find out when it is maximum, what should I do? At what angle? I want to find out what is the angle at which this is maximum. What should I do?
Sir, differentiate with respect to alpha and equate it to 0.
Correct. I think that's precisely correct. So what you can see is that for the sine, but before I do the differentiation, I just want to put this in a slightly different form, in the same form as I have put this, which is in terms of sine of 2 alpha and cos of 2 alpha. So you will remember that so just as a aside, you know that sine of 2 alpha is just equal to 2 sine alpha cos alpha, and we know that cos of 2 alpha is equal to squared alpha minus sine squared alpha. So I can use this to put both of these terms in terms of sine on cos of 2 alpha. Just the algebra will become easier when we want to do the derivatives. So instead of having squared terms, we'll get so this means that we can put this also in terms of the other way around. So this is equal to, we can say it's 2 cos squared alpha minus 1 and it's also equal to 1 minus 2 sine squared alpha. So we can write cos squared alpha as just equal to cos of 2 alpha plus 1 divided by 2, and we can write sine squared alpha is equal to cos 2 alpha minus 1 divided by 2. So this is what we will do, and so then our sigma x prime will just become equal to sigma xx into cos of 2 alpha minus.
Sir, 1 minus cos 2 alpha upon 2.
It is 1 minus cos. Correct. Perfect. Correct. And then for sigma yy also, I'll use the correct formula, 1 minus cos 2 alpha divided by 2. And then the third term is sine of sigma xy into sine of 2 alpha. So now if I combine this, you can see this is equal to sigma xx plus sigma yy divided by 2 plus sigma yy minus sigma xx divided by 2 into cos of 2 alpha plus sigma xy into sine of 2 alpha. So this is what we get. And now we'll do the thing where we simply take the derivative of sigma x prime by with respect to alpha and put it equal to 0. So the first term goes to 0. Derivative of cos of 2 alpha will just give you minus sine 2 alpha into 2. And this
Sir,
one will give us.
sir, sorry to interrupt, but the first term is also 1 minus cos 2 alpha, or like the sigma axis coefficient.
Which one?
Sir, the first term, sigma xx into cos 2 alpha minus 1 upon 2.
It will be plus, no?
Yeah.
Yeah, that is plus. So, but I did it correctly, no? The next line is correct.
Yes, sir. Yes.
There I made a mistake. Okay, yeah. Good, thanks. You feel free to interrupt anytime. And then, so this one will remain the same. So this will give us plus 2 sigma xy cos 2 alpha, and this must be equal to 0. And I'm going to call this as alpha star because that's the special angle at which this is either maximum or minimum. And because we've done all this, so now you can see that if we simplify this out, we'll get tan of 2 alpha star, not alpha star, alpha m I think is what I'm using in my notes. Yeah, I'll call this alpha m, not alpha star. So it's either maximum or minimum. So tan of 2 alpha m is just equal to 2 sigma xy divided by sigma yy minus, have I done it correctly? So this is the other way around. This is, it should be correct. This cos alpha is positive here and negative there, so I made a mistake there. And so I just remove this. So then this becomes sigma xx minus. So this is what you get. So if you are given the components xx, yy, and xy, I can tell you what is the angle at which the solution is either maximum or minimum. And you can see, since tan is a periodic function, so the solutions are whatever you get plus pi. So then you will have the solutions to this. You will have actually at least two solutions. They will be alpha m and alpha m plus pi by 2. So those will be the two axes, and one of them is maximum and one of them will be minimum. And one of the things that you can easily see is from this formula, supposing sigma xy is 0, then what will be alpha m?
Sir, 0.
So one solution will be 0 and the other is pi by 2. So then what will happen is, what we are saying is that if the shear stress is 0, then the original axes x and y, those are the principal axes. When you say alpha m is 0, that means that this angle is 0. If this angle is 0, that means x prime is the same as x and y prime is the same as y. So then x is the major principal axis and y is the minor principal axis. So it will be maximum along x and minimum along y. So this is what you get. And actually you can also prove that if we substitute now in sigma x prime y prime, so we know this. So if we take out cos of alpha common from here, cos of 2 alpha, so here you will get sigma x prime y prime of alpha m. This, I'm going to take this formula and take cos of 2 alpha m common. So then what I will get is cos of 2 alpha m, and I'll substitute for tan alpha m using this. So when I take that common, then I'll have here tan of 2 alpha m plus sigma xy. So this is sigma yy minus sigma xx divided by 2, and then I'll have tan of 2 alpha m, which is 2 sigma xy divided by sigma xx minus sigma yy, and then plus sigma xy. So you can see that this, when it cancels out, it gives you -1, 2 cancels out with 2, so you have -6 sigma xy, and so this is equal to 0. So along the principal axes, so when we are working with when the angle of the principal, when the angle of the axis is alpha m, those are called the principal axes. And so for the principal axes, these are the coordinate axes, x prime and y prime. you have sigma x prime maximum comma minimum, and sigma x prime y prime is equal to 0. So this is the property of principal axes that in that coordinate system, when you have rotated by alpha m, then our tensor in this new coordinate system is just sigma x prime 0 0 sigma y prime y prime. So it just becomes a diagonal tensor. So this is the whole idea, that you rotate it to get a diagonal tensor. So why do we do all this? It'll become clear in a little while. So this essentially the reason that we want to understand how the normal stress and the shear stress vary. It goes back to this idea that our stresses in the system are all frictional, and the frictional force is dependent on the normal force and the shear force. The ratio of those two is a constant. So similarly, when you have a continuum, we will see that really at the point of yield, that is when the material just starts yielding, the ratio of the shear stress to the normal stress becomes equal to the yield stress. But it's not just any shear stress or yield stress, but you will see that it's at a very particular value of the shear stress and yield stress that it is 0. So now let's just go a little further ahead. We have now found out the principal axes, and the next thing we'd like to do is we'd like to now sort of be able to see how can we really go one step further. So we can express now essentially what we'd like to do is calculate what would be the maximum. So we have found out what is the angle at which the stresses are maximum or minimum. Now we want to find out what are these actual values of this sigma xx max and sigma x. So what we have to do is then what we can do is we can just substitute for tan of 2 alpha m, which is given in terms of this, into these equations. We have got these equations, and so we can just substitute into this equation, and so then everything, the sigma max will come in terms of this. So the next thing is the principal stresses, which is maximum and minimum values of the stress. So we already know that we can easily find out this thing, but we'd like to just get a simple formula just in terms of sigma xx, sigma yy, and sigma xy. So we would like to get expressions for sigma max and sigma min in terms of the given components, which are sigma xx, sigma yy. So these are given to you. They'll be just numbers. And how would you do that? Well, we have everything in terms of sine of 2 alpha and cos of 2 alpha. So we can easily write down sine alpha in terms of tan of alpha, because we know already tan of 2 alpha m, this is already here, we know it in terms of these quantities. So now let's see what is sine of 2 alpha m. Well, if you do little bit of trigonometry, then you can easily show that tan of 2 sine of 2 alpha m is tan of 2 alpha m divided by 1 plus tan squared of 2 alpha m raised to the power half. Do you agree with this? So I can just,
Yes, sir.
so you can easily work it out, because sine is just a tan is just sine by cos. So this is sine squared by cos squared. So this becomes cos squared plus sine squared divided by cos squared. So that's 1 by cos squared. So 1 plus tan squared is just 1 by cos squared. Square root of that is cos. So then when you take it up there, so it's tan multiplied by cos, so it'll give you sine. So this is the simple thing. You can, I'm sure you would have done it many times. Now we can substitute for tan of 2 alpha m. We know that it is just 2 sigma xy divided by sigma xx minus sigma yy. And then over here, I'm going to just go the other way around. So this will be 1 plus 2 sigma xy divided by sigma xx minus sigma yy whole square raised to the power of half. Okay. I'm sorry, raised to the power of minus half. So now, in some sense, this cancels out, because since it's raised to the power of minus half, so so this just becomes equal to, this remains the same. And here now, if I take the thing in common and do it, so just skipping one step, this is sigma xx minus sigma yy whole square divided by sigma xx minus sigma yy whole square plus 4 sigma xy squared, and this whole thing raised to the power of half. So now you can see these two things just simply cancel out. But the only thing we have to be careful about is that, is sigma xx larger than sigma yy or not? And so let's assume that sigma xx is larger than sigma yy. So then the term inside is positive. So then when you cancel this out, it will be 1. Otherwise, it may be minus 1. So yeah. So you can easily do this thing. Now what else? So we have sine of 2 alpha. In this we have done this one. Now we need to do cos of 2 alpha. So similarly, cos of 2 alpha is just sine of 2 alpha divided by tan of 2 alpha. So you just get this is just the same, but you have to just do 1 divided by 1 plus 10 squared 2 alpha m is to the power of half. And if we simplify this, then this is just equal to just the absolute value of sigma xx minus sigma yy. So basically the front factor will be missing, the rest is the same. Divided by sigma xx minus sigma yy. And now if I take both of these and I substitute in there, then what I will get is I will get, so I want to now substitute for sine of 2 alpha m and cos of 2 alpha m in this expression. I'm sorry, in this expression for expression for the normal stress. So the first term is as it is. Here it will be cos of 2 alpha m. Here it will be sine of 2 alpha m. And so what we'll get is, again, I'm going to skip out a little bit on the algebra. I'll get sigma max, sigma min. So here, what this term is, sigma xx minus sigma yy whole squared square root. This is nothing but, I can remove this from here, remove this, and I can simply put this as square root. So, in this one we are taking, so this just becomes absolute value because it's squared and then square root. So if you're taking the positive root of it, so it's just this. So that's why you get this. And then you will get sigma max minus sigma min is just equal to, I know we are almost at the end, but I'll just write this formula down, in which, so I've taken the earlier formula, I'm just substituting for these. So this is there into cos of 2 alpha m, which is just modulus of sigma x minus. So this is the second term where there's cos of 2 alpha m. Just hang on. And then the third term is where we substitute for sine of 2 alpha m. And that gives us plus 2 sigma xy whole squared divided by sigma xx minus sigma yy whole squared plus 4 sigma xy whole squared raised to the power of half into sigma xx minus sigma yy divided by So this is like saying what is the sign of this. If sigma xx minus sigma yy is positive, then this will be 1, otherwise it will be minus 1. So if we now do the final simplification of this, and this I'm going to end after this one. And this is just like doing little bit of algebra. So the first term just remains as it is. This just stays as it is. Now the second term can be plus or minus depending on whether sigma xx is larger or sigma yy is larger. So this term we can write down, and so we'll write it as plus or minus. Could be either of them. And then if you see this, this will be sigma xx minus sigma yy whole squared, and this is 2xy, I'm sorry, yeah, 2xy whole squared, and if you take the half out, so then this term will be the same as that in the brackets, and so when you take the square root of it, I think I'll leave it for you to really work this out. You'll see that these two just simplify to this. So here you have for the maximum value of the normal stress and the minimum value of the normal stress, we get this simple formula in terms of the components of the stress tensor. So this is the basic idea, that if we go right back, what we started with today is we want to try and look at a system which is dominated by friction. For that, we need to be able to calculate the stress tensor on any plane in the system, and this we did by looking at these components, and so we can calculate the shear stress and the normal stress on every plane, and then we can find some two special planes on which the normal stresses are maximum, that is sigma x prime is maximum or minimum, and on that your sigma x prime y prime, the shear stress is 0, and your stress tensor just becomes a diagonal stress tensor. Now then we just did little bit of algebra to get what is the actual, when you are at alpha m, what is the magnitude of the maximum and what is the magnitude of the minimum normal stress, that is given by this in terms of the components of the stress tensor. And just as a check, you can tell me what is going to be the normal stress when sigma xy is equal to 0. So if sigma xy is 0, then you can see that the term in the square root will just be plus or minus sigma xx minus sigma yy by 2. So you'll either get sigma xx or sigma yy as required. So let me end today with this, and I'll see you tomorrow. Okay, thank you.
Thank you, sir.
Thank you, sir.
Okay, bye bye.